Good day everyone, welcome back to Learning to Understand Electrical Principles. Today we're going to be discussing parallel circuits. So last time we discussed a series circuit. That's a circuit where the current will remain the same throughout the entire circuit, while the voltage will change. Now we're going to look at a parallel circuit to understand how this works. So, once again we have our voltage rise, and this is our total voltage, or our source voltage. This creates a current. Now, what you notice is at this point, this current splits. Now, this split is going to be equal to something we call KCL, or Kirchhoff's current law. And that states that the current going into a junction is equal to the sum of the current going into the junction is equal to the sum of the current coming out of the junction. So this is going to be IS. It's going to be I1. It's going to be I2. So IS is going to be equal to I1 plus I2. Now, why is it the sum? Well, if we think about electrons flowing through this, we're not going to lose electrons at any stage of the process. It's like water in a giant tube that splits. Some of the water is going to go the one way, some of the water is going to go the other way. And that water is going to be dependent on the size of the tube, the amount of water going through each one, which is based on the resistance, because the size of the tube is the resistance. But you notice it splits, and the total amount of water that went into that tube it's just going to split then. That's why it's the sum of these, because the total amount of actual current will remain the same. Then when these two join back up here at this point, well, then the total currents going into the thing is I1 and I2. So these are the ones going in, and then we're going to get an IS out. So what this means is that in parallel, the current of the circuit is not the same. It's different in each parts of the circuit. And now this current will once again cause voltage drops across the components. Well, that's supposed to be a minus. This creates a voltage drop. Actually, there we go. This creates V2 and V1. And if I actually go and replace this with red, so I can put R1 and R2. Now, if I take a highlighter, let's take a very nice visible color. Let's take orange. If I highlight this entire section, up to that resistor, is any of the potential actually used up? While the current splits, yes, at this point. Has our ball actually moved? Is anything used up potential at all? No. Our potential will remain the same. So this entire section has the same potential of Vs. And then if we look at this part, and let's color that in I guess a yellow, because every other color's really been used. So if we cover this in yellow, well, we notice that goes to the source, so that must be 0. But you also notice none of these are being used. So this entire branch is equal to 0. So that means that the potential at these 2 points are the same, and the potential at the end 2 points are the same. So that means V1 will have the same potential as V2. And that will actually have the same potential as Vs. So when we look at a graph, a diagram like this, instead of the series circuit where it's a bunch of steps, what a parallel circuit looks like is just one drop to zero. So this is the drop of V1 and V2, and this is the drop of Vs. And you notice that these all three have the same drop. So therefore, the voltage remains the same throughout. And now, if we want to get the relationship of our resistances now, oh, by the way, this is called a node. And a node or a junction. This little part here is the junction, but a node is something that has the same voltage throughout, but the currents aren't all the same. Well, the currents can be the same, but the main continuation is that it has to have the same voltage throughout the entire section, the same potential difference. And that definition you should keep in mind, because when we get to later sections, knowing what a node is will be very, very useful to learning to understand circuits. So now we know our formula for the total current is 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 equal to I1 plus I2. So resistance is now equal to our voltage over our current. So if I divide by voltage throughout, because the voltage remains the same, then I should get 1 over my resistance. And that'll be my total resistance, which is equal to 1 over R1 that's R2. So therefore, this will be our formula now for the total resistance of a parallel circuit. And now there is another formula that some people use. I prefer to use this one in most cases, but I will admit this one does have its benefits sometimes. Is if we say R1 times R2 over R1 plus R2. So this formula has its uses, but one thing you have to seriously remember is this only works when you have two resistors. If you have three resistors, there is a different formula to use. So do not use this if you have more than two resistors. Do not, because you will get the answer wrong. You cannot just say R1 times R2 times R3 plus R1 plus R2 plus R3. You will get the question wrong. If you're working with three, rather use this one. Now, just like with voltage in series, where we had something called the voltage divider rule, we also have something called the current divider rule, because current does split. Now, how we calculate the current in, let's say, branch 1. Now, a branch, by the way, I forgot to mention this in my series video, but a branch is something that has the same current, but it might have different voltages across it. So a branch is basically a series circuit. It's the series part of the circuit. The current will remain constant while we have different voltages through it. So if we want to get the current in branch 1, so this would be our branch, we know that voltage of 1 is also equal to the source voltage. So this will give me I1 R1. And that is equal to IS RT. Now, this will essentially just give me I1 is equal to IS RT over R1. Now, one thing you need to remember about this formula when compared to the voltage divider formula is that the total resistance is at the top. And why is the total resistance at the top? Well, the amount of current in this branch has to be smaller than the total current, right? Because it's a sum of it. So, the total resistance, when we look at this formula, and you actually start using this formula, you'll always notice that the total resistance will become less than the resistance of each of the branches. It will always be less than the branches. So therefore, this will actually become the smaller number, the smaller quantity. And so this will be a fraction that's like 0.5, let's say. Because RT is always smaller, it's going to be 0 point something, which leads it to being less, which leads us to being times by a number less than 1, and then we get our number. I'm not sure if I explained that well, but basically, since the total resistance is always lower, so we're going to get a fraction, and that means we'll get a lower number here. With voltage and a series circuit, that number is always going to be greater. The total resistance will always be greater than the resistances it's made a part of. So that's why it's going to go at the bottom. So we get a fraction, which allows this number to be smaller than that one. Now, that's pretty much all you need to know when looking at a parallel circuit. So the current will change throughout, but the voltage will remain the same, and resistance is this formula. Oh, one last thing is we do have another formula that we can use. IS, and this is one a lot of people use, and it does annoy me a bit, but R1, but this is equal to R2 of R1 plus R2. Now this comes from using this formula for the total resistance. And now you notice that instead of being in terms of R1 now, it's in terms of R2. So that can trip a lot of people up. And this formula, once again, is only used if you have two resistors in parallel. If you have more, don't use it. Now, the thing to remember though is this formula is more useful if you only have two branches. So when I say two resistors, I mean two branches, because you can obviously have multiple resistors in the same branch. And then you'll just say like R1, R2, R3 plus R4, R5, R6, and just treat them as one resistor. But that aside, and that's a bit of a tangent, this formula is really useful if we haven't calculated our total resistance yet. If you get a question which has two branches and you haven't calculated your total resistance yet, then this formula is often much faster. But in majority of cases in question papers and all these sort of things, they ask you to calculate RT first, or you had to use RT in a previous question, and then you will always use this formula. Always use this formula, because it is faster and it's less likely to mess up. Because here a lot of people think they're going to plug in the value for R1 instead of the value for R2, and they will get the question wrong. So If you're unsure and if you're scared to use this formula for every situation. But this formula is better if you don't have your total resistance already and you only have two branches. Thank you for your time.